Yay. Okay, folks, welcome to another fabulous day of Calculus 3. So last time, what did we do? We did the cross product. That's right. And what's the cross product? Well, it has a cross in it. And when you take the cross product of two vectors, you get a vector. And the vector that you get has some very special properties. It is orthogonal to the two original vectors. And here's some more properties that we did all last week. These are wonderful. And so we're going to go continue here with example 2 that tells us to go find a vector that's orthogonal to both of these vectors. So what do you think letter A is going to involve? Does anybody have a quick guess on what I should even do for letter A? Quick guesses.
Subject.
Anybody have a clue? What should I do for, how do I find a vector that's orthogonal to both the u and the v here?
Is it the projection of u onto v?
No, there's no projections involved here. That's not going to get us something orthogonal to the two originals. I'll give you all a hint, okay? I'm going to give everybody in the room a hint. You see my hint?
Yeah.
Yeah, a vector that's going to be orthogonal to the two original vectors is going to be the cross product of u and v, and that will give you a vector orthogonal. Now, in case you forgot, let's go back to the first page of this lecture. May I remind you of this picture here, that here's u, here's v, and then this vector here, woo, that guy right there, using the right-hand rule, that's how you figure out which way he's oriented, is a vector that's making a 90-degree angle, the AKA orthogonal, to the two original vectors. Everybody see that? And that's why we got to do the cross product for this example 2 part A. Okay, so I'm going to use the 3x3 determinant method. And remember, on all quizzes and exams, I require that you use the 3x3 determinant method. Even if there's another way to do it, I'm not going to give you credit. Okay, I'm telling you right now how to roll. So this guy, tell me what I'm doing wrong when I write his components there in the second row.
The j is 0.
Very good, very good. The j is 0 because it's not there. It's understood. But sometimes if you're, really scared and nervous taking a quiz or an exam, you may accidentally copy it down wrong. And then you know what happens when you copy something down wrong? Some of you found out the hard way on Monday's quiz is like, the whole rest of the problem goes down the tubes. Oh, I've done that. It happens. I usually give some partial credit for process, but you want to try to be mindful and careful when you're doing your exams and quizzes. Okay, so here's the deal. You're going to have a 2x2 I hat minus 2x2 j hat plus 2x2 k hat. We're expanding along row 1. And the 2x2 that's multiplied with the I hat here, that's a 2x2 determinant. You block out the row and column that I hat lives in and copy down those elements. Similarly for the j and for the k, and then you do the little process of finding a 2x2 determinant of a matrix. So you multiply along the major diagonal minus the product of the elements along the minor diagonal. It's important that you do that right, because sometimes I see people do a plus and then all hell breaks loose. So here I've got negative 3 times 2 is negative 6 minus 2 times 1, and then plus, and then here I'm going to do major diagonal, negative 3 times 2 minus 0 times 2 is 0. And then this is going to be what? Negative 2i minus a minus 8j plus a negative 6k. And I like component form, but that's my just personal preference here. So my final answer, whoop, I'm running out of room there, is negative 2, 8, negative 6. Okay, so that's letter A. Now we're going to do letter B. Well, what about finding this area of a parallelogram that has two adjacent sides, u and v? Okay, so if I draw a picture, let's say this is u. I don't know what they really look like. There's some vectors in space. If you can imagine those as two adjacent sides of a parallelogram, so I'll draw in the other two sides with dotted lines, we want the area here. And good news, we don't have to do much to do letter B, because if you look back at one of these theorems on the previous page, it says, and this is problem number 4 property here, if you take the magnitude of the cross product of two vectors that are non-zero, of course, and not pointing in the same direction, it will give you the area of a parallelogram having U and V as adjacent sides. Fantastic. Good news. We already did part of the problem then, because we already did U cross V. So all we have to do is take the magnitude of our U cross V, and then we'll have our answer. Fantastic. So here's our U cross V. So the magnitude of that is going to be the square root of the sum of the squares of the components. Whoop. And what do I have here? Square root of 4 plus 64 plus 36. Oh, and that's square root of 104. Now, if you leave your answer as that, I'm going to, my math lab might be okay with it, or it might not. You have to read the directions. I'm going to take off a point regardless, because anytime a radical can be simplified a little bit more, not give me the decimal answer. I claim that 104 happens to have a factor that's a perfect square. And you always want to find the largest factor that's the perfect square, so you completely simplify. Good news, square root of 4 is 2. Final answer, 2 square root of 26 square units would be the area of that little parallelogram. Questions? Everybody okay with this?
Yeah, looks good.
You think it's okay? All right, so letter C. Now the last thing, the letter C, is find the area of the triangle that has sides U, V, so U, V. And then remember when I did subtraction, U minus V is this vector that's connecting the two tips of the original vectors. And so they want this triangle. But see, folks, that happens to be, if you compare it to the parallelogram diagram I have right above it, that happens to be half the parallelogram. So the area of a triangle having U and V as adjacent sides of the triangle, and then U minus V being the third side, is simply 1/2 of the parallelogram area. Fantastic. And since we already got the parallelogram area, we're just going to take 1/2 of that, oops, 26, and reduce, the 2's cancel, and your final answer is your triangle has an area half the parallelogram, square root of 26 units, okay? So here's a little handy fact for you. Anytime you are asked to find the area of a triangle, it's half of a parallelogram, that if you make a copy of itself there. So I hope that helps the understanding there. And I think we're ready to move on. So let's take we're going to still use some of the theorem properties here. That's what some of these examples are about. So here again, we've got some space vectors, and they're giving you some information about the space vectors. They're telling you, okay, they're not giving you the components, but they're going, all right, the magnitude of one of them is 25. That's, great. The magnitude of the other is 30, and the angle between them is 120 degrees. Fine. So you can imagine that this would be a 120-degree angle here. Okay, so they want us to find the magnitude of U cross V. Well, wait a minute. I thought you wanted us to, when we find a cross product, you got to do the 3x3 determinant method. Well, you only do that if they give you the components for U and V. So how do I even get the cross product if they gave me these pieces of information and not the components? Don't try to go and retro engineer finding the components. I've seen students do that for a problem like this, and it's a nightmare. And even if they finally get the right answer, I give them 0 credit because they wasted all that time. And if you're wasting time when you have at your fingertips some properties that are right there for you, then I can't give it to you. So take a look at property 2 here in this theorem. Check it out. We don't even have to go find the cross product. That just tells me, boom, the magnitude of the cross product is automatically going to be this sine of the angle between them multiplied by the magnitudes. That's wonderful, because I hardly have any work to do. And I immediately get access to the magnitude of the cross product without having to do any work. So I don't need to find that cross product. I'm just going to go, hey, the property told me that I'm going to just go sine of the angle between them and multiply their magnitudes together with the sine. I just need to figure out what the heck is sine of 120 degrees. That might be the hardest part of the whole problem, truthfully. What the heck is sine of 120? I think it's square root of 3/2. And then you multiply that with 25 times 30 and, give me an exact answer. So it turns out after reducing, the exact answer is 375 multiplied by the square root of 3. Yay! And we win. Now, here is a hard problem that some people who refuse to learn the right-hand rule, they get hurt by this. And I love to put that kind of problem on exams, because I like to see if people know the right-hand rule or not. Now, I'll tell you a funny story about the right-hand rule. Many years ago, before probably anybody in the call was born, I was an undergraduate at UC Berkeley, and I was taking a physics class with like 300 other students, and we had to take the final. So we're all in this huge room that's sort of terraced. So, like almost like a stadium room is huge at UC Berkeley. And there's all of us stacked into this room, and we're taking our final, and their finals are 3 hours long. And it's a long final, and it's hard, physics, So about halfway through the final, I just wanted to take a quick break and breathe. And I looked around the room, and it was the funniest thing. If you could look at my video right now, there were people in the room that were like almost turning their bodies upside down and trying to use their right hand and like doing this and doing that. And it was nuts. And they were all trying to figure out, which direction this cross product, because you use cross product in physics and you use the right-hand rule. And I have that visual just burned into my brain and I even thought to myself, don't ever forget this, because it's hilarious. So I don't know if you have any memories like that where you look back and it's just like yesterday. So that's my funny story about the right-hand rule. Now, how do you use the right-hand rule here? You're trying to find V cross U. So you have to think it is going to either point out of the page or directly into the page. There's only one of two ways that cross product could be if U and V actually are flat on the page. So you're going to have to curve your fingers first through V, because they said so here. It starts first. And you curve and curve and curve, and then you close and make a half fist. And then you have to determine which direction your thumb is pointing. Is it pointing into your page, or if you're taking notes on the table or whatever, or out? Okay. Anybody have an idea?
Into the page?
Yes, that is correct. It is into the page. All right. And we're done. True or false? U dot product, that's a dot product, with the cross product, so this right here is a vector, he's the cross product, is equal to 0. True or false? Now remember, a dot product is equal to 0 if what? So if you have two vectors U dot V, if this is true, what does that mean that the relationship between the two vectors is? Does anybody remember?
Is it that U is equal to V?
No.
The two vectors are orthogonal.
Yeah, I heard it. I heard somebody say they're orthogonal. They are orthogonal with each other. Okay. So that is a true statement. And if you didn't learn that from section 13.3 yet, ooh, the rest of the semester is going to be painful. That's like a handy fact you got to keep under your hat at all times. Anytime the dot product between two vectors, whatever the vectors are, is equal to 0, you're guaranteed that they're orthogonal, that, essentially they're perpendicular. Although in 4 or 5 dimensions, you can't even speak about something being perpendicular. So that's why we use the word orthogonal. So here, if this vector and this vector, their dot product gives you 0, they're supposedly orthogonal, right? Is that even true? Is the cross product of a vector u and v orthogonal to the one of the original vectors u?
Yes.
Why?
Because of the example we did on the last page, that it means that it was orthogonal.
Yeah, but even more than that. By definition, people. By definition, this u cross v is orthogonal to either one of these two original vectors. So it's going to be true that the dot product between either of the two originals and this cross product will be 0 because you got orthogonality going on there. Yeah?
Yes.
Okay, folks, these are some basics of vectors that I really need you to be mindful of. And I know it's hard to learn remote and it's so many facts and figures and you're going really fast and, oh, it's going to go faster, trust me. Yeah, I didn't think Calc 3 would be like this. Ooh, yeah. So you got all these relationships that we're laying down here in this vector module are important. Okay, so it is a true statement. It's true for reals, for realsies, okay? Now, let's do some weirdness. Let's take the vectors I, j, and k, and if you'll recall, I is the vector 1, 0, 0. J, if we're working in 3D, because cross product, you do work in 3D. J is understood to be 0, 1, 0, and k hat is understood to be the 0, 0, 1 vector. Is it true or false that I cross j is equal to k? Now, folks, you could do this the slow way. Like, here's the slow way. Well, okay, I cross j. First, you do the 3 by 3 determinant. You actually put ijk across the top. And then I will go in the second row, and j goes in the third row. And then I'm going to go d I hat minus j hat plus k hat. I'm going to do this really fast. Okay, so here 0 minus 0, 0 I hat, minus 0 minus 0, 0 j hat, plus 1 minus 0 is 1 k hat. So that looks like it's going to be k hat. Yeah? True. Now, is there a quicker way to do this? Yes. If you're willing to do the right-hand rule and you understand it, I would say you wouldn't even really have to show me the slow motion way. So here's the quick way. Draw the x, y, and z coordinate axes. Okay, in the rectangular coordinate system. I hat is understood to be pointing, it's a unit vector pointing in the positive x direction. J hat is over here pointing in the positive y axis direction, and k is pointing straight up in the positive z axis direction. So if you take your fingers and start curving them through and then close your fists down here, I'm sure these are fingers, first through I, then through j, your thumb should be pointing straight up in the k direction. So it is going to give you k. Now, what about I cross k? Well, you can do the same thing if you are, courageous enough to get this right-hand rule down. You first start your fingers going through the I, and then, and I should probably get sort of behind the paper because you're going to want your fingers to start curving first through I. So here's your fingers. And then they're going to go through K, and then they're going to clamp down and have your thumb sticking out. And I claim it's going to point in the negative J direction. So this is false because the answer should be negative, or going in the opposite direction of J hat. Okay, and if you don't believe me, you can of course do the 3 by 3 determinant method and do it the slow way and prove to yourself that you get the opposite of J hat. And similarly, negative J hat crossed with K, that you got to do your fingers here, is negative I hat. That actually is true as well. All right, so these are things you do. Now here's a meme for you because I think we need a little bit of comedy. Hopefully that'll make you smile a little bit. I thought it was hilarious. Does the right hand rule with the left hand? All right, anybody smiling at least, or are we all glum today? What's going on?
Trying to keep up.
Trying to keep up. Well, write faster. Okay, more applications of the cross product. I'm going to go over the triple scalar product, aka the box product. And I alluded to this being called the triple scalar product and also called the box product when we did our notes back here. So this was one of the theorems. And I said, hey guys, did you know that this U dot V cross W, which is the same as U cross V dot W, there's a dot product and a cross product in the same expression. It's called the triple scalar product, also known as the box product. Now, folks, I'm going to most likely give you one of these problems on a quiz or exam because I'm into the triple scalar product and you should know what it is. And I'm going to tell you the slow way to do it and then the fast way to do it. And if you do it the slow way on your exam or quiz, even if the answer is correct, I'm not going to give you full points because that means you didn't pay attention. And you like pain. So this is essentially U dot product with V cross W. That's what it is. Okay. Now, if you want to do it the slow way is do it like this. Like first go get the cross product using the 3x3 determinant method, la, la, la. And then once you get him, then do the dot product and then you get your answer. So the slow way is, you do your cross product, then do the dot product. And then you get your answer. Okay, fine, you'll get the right answer. And I'm not going to give you full credit because you're not doing it efficiently. I'm going to give you the sweet, cool beans way of doing a box product fast. Okay, so how do you do it fast? Well, you don't do it slow. The quick way is basically saying that this U dot V cross W, you're not going to do any dot product or anything. You're going to set up a 3x3 determinant. But instead of putting I, J, and K in the first row, U is going to go in the first row, his components, that is. And then V is next. And then W's components are last. And then this is actually a legitimate dot product. So what you're going to do is you're going to expand along row 1 like we did when they were I, J, K. So you're going to go 2 by 2 multiplied with U1 minus a 2 by 2 multiplied with a U2 plus a 2 by 2 determinant times U3. And once again, block out the row and column that U1 lives in, and the elements in this little 2 by 2 are V2, V3, W2, W3, and over here, block out the row and column that U2 lives in, and look at the elements that are left standing, V1, V3, W1, W3, and then finally, block out the row and column that U3 lives in. And then you got to do these little 2 by 2 determinants here. So you're going to go, okay, the product of V2, W3, whatever that number is, minus the product along the minor diagonal V3, W2, and multiply that with the pure number U1, and then minus, and then you're going to do this here, V1, W3 minus minor diagonal V3, W1, U2, and then plus. Here, the major diagonal is V1, W2 minus the product along the minor diagonal V2, W1, and you'll multiply that with U3. And you're going to get a scalar, pure number. Pure number, people. A scalar is a pure number. Fine. Now, does that pure number represent anything? Yes, it does. It's really cool. It's really cool. And we're going to look at what you can use the box product for. It turns out it's the volume of a box. And if it comes up negative, just take the absolute value because you don't want volume to be negative, okay? So it turns out that if you have a U, V, and W vectors all making adjacent sides, or I should say edges of what's called a parallelepiped, which is just a fancy schmancy name for a rectangular box that's pushed over a little bit, has a little bit of a shear to it, slanted over. And so the volume is actually equal to the absolute value of the box product. Now I'm going to do a quick little mini proof. Why is this true? So let's do a little proof and why the volume happens to be the absolute value of the box product. So this weird solid that you see here, the area the volume, which is what we're trying to find. And if you're an engineer, you care very much about this, so pay attention. These are the kind of applications that, they're right in your wheelhouse, okay? You want to get the area of the base of the solid. So the base is the bottom, essentially, that's lying flat on the ground. And then you want to take whatever that area is and multiply by the height. Now, the height is not the length of U. The height is this right here. The height is if you dropped a perpendicular from this Z coordinate of U down, that gives you the height. So like if I drop this perpendicular down from U to the base, that right there is my height. So height. Now, how do you get the height? We're going to use projections. If we project U that onto the cross product of V cross W and then take the magnitude of that projection, that will give us the height. Now, what do you mean? So we're going to V cross W, here's V and W down below here. This vector here they're showing you is V cross W. And so if we project U onto V cross W, we will get a vector that's just as tall as our height. Okay, fine. So, and then what's the area of the base? Well, the base down here is a parallelogram where V and W are adjacent sides. So I claim from a previous theorem we just did, that's just going to be the magnitude of V cross W. Okay, so there's a magnitude, and then we have another magnitude, multiply those two magnitudes together, boom, we get the volume. So let's save this for later, and let's look at this. Let's do a little bit of scratch. I'm saying scratch, like, I'm just showing you sort of, all my thinking here. How do you get this vector, which I'm going to denote projection of U onto V cross W? So first, let's do projection. And you're supposed to know how to project a vector onto another vector. Okay, that's key, and you're going to do that, this coming week's quiz 2. That starts on Sunday and is due Monday, and you're going to actually do it the rest of the semester. So if you recall, you're going to have a scalar times a vector, where the vector will be the cross product, and so the numerator of the scalar is going to be a dot product of those two vectors divided by the magnitude of V across W squared. So this is what the projection is going to look like, okay? I know it's pretty messy, but what I love about this little mini proof is it kind of forces you to really think about your previous knowledge from section 13.3. And math is a vertical subject. What you learned last week, you need it for this week. Forget trying to move forward without knowing what we just did. So now if I look at the projection of U onto V cross W, I'm going to take this big old vector and just put these double bars around it. That's how we denote magnitude. Now, when you take the magnitude of a pure number, which this numerator is, that numerator is just some funky scalar, you're just going to get the absolute value of that funky pure number. Now, when you take the magnitude of a magnitude, like here, we're taking the didn't mean to do that. Here's a magnitude, and we're taking a magnitude of something in their magnitude. It doesn't change it at all. It's still a magnitude. Okay, so then what? What do we get? Well, we get absolute value of the pure number, which is a dot product. And sometimes dot products can be negative, so we want to make sure we get a positive here because it's magnitude. And then this just turns into magnitude of that vector. And the denominator is still the magnitude of V cross W squared. So you see that I can reduce this to lowest terms? And so after reducing, I'm saying that the height of the parallelepiped, let's say that fast 50 times, this is your height. So finally now, I'm going to finish this up. So my volume is going to be the area of the base, which was the area of a parallelogram, times the height. So I'm just going to substitute here. Got the absolute value of that pure number divided by magnitude. Okay, and then guess what? Boom, reduced to lowest terms. Final answer. Woohoo! Triple scalar product, also known as box product. Okay, and QED and a proof. If you understood that, congratulations. You've come a long way, baby. You're getting your vectors down here and looking at some cool applications. All right, we're going to keep moving on. Got a lot to do today. We always have a lot to do. You know, I don't see you for a week. So remember, we have President's Day weekend this weekend. Have a good time. Let's study. So we're going to do the volume of the parallelepiped problem, an actual example with actual numbers. So let's say those three vectors are adjacent edges of a parallelepiped. You know, what the heck is a parallelepiped again? It's sort of a sheared box, you know, that's sort of leaning over, like that. So get that guy's volume, fine. Now, if you wanted to do it the slow way, you could get the cross product of V and W and take the dot product of that with U and then take the absolute value in case it's a negative number. But I'm not gonna. I'm gonna set up the 3x3 determinant that I showed you, the quick and dirty way, which is U components go along the top row, V is in the second row. And by the way, it doesn't even matter what order. You could put any of these in, like, oh, I want to put W at the top and V second, U at the bottom. Fine. Okay, I might get a positive, and then when you rearrange rows, you'll learn in Math 254, it does affect the determinant. It may change the sign. So I don't want to get into that now, but it could happen. But as long as you have absolute value at the end, we all get the same answer. So I'm going to go 2 by 2 times 3, because I'm expanding along the top row, minus a 2 by 2 multiplied with -5, plus a 2 by 2 times 1. So what's the 2 by 2? It'll have elements 2, -2, 1, 1. This one will have 0, -2, 3, 1. Oops, don't copy them down wrong, because then you'll blow the whole problem. And then here, major diagonal is 2 minus the minus diagonal, the minor diagonal. And that'll be that minus 0 minus, oh, there's a lot of negatives running around here. 0 minus a -6, I think so, times -5 plus 0 minus 6 times 1. Good Lord, what do we have here? I think we have 4 times 3 minus 6 times -5 plus -6 times 1, which is -6. And this is going to end up being 12 plus 30 minus 6. I get 36. And this is units cubed because we're doing volume. I don't know what the units are. They didn't tell me. So some units cubed because it's a volume. Okay, and I'm done getting the volume of one of these parallelepipeds. Questions?
Yes. Did that say 30? Oh,
Sorry.
does that say 36 U cubed?
Means units cubed.
Thank you.
Professor, could you repeat why it is that we multiplied it by the 3, the -5, and the 1?
Because that's how you take a 3 by 3 determinant.
Okay.
And if you take Math 254, you'll learn a lot more about determinants.
Okay.
Okay, so if you want to take this offline, I'd be happy to do, and we can discuss further in the
Yeah, I'll see you in office hours.
But I do want to say that I'm not going to go too much more into detail in my office hour, other than to say you need to accept it.
Okay.
It's like, well, I don't want to hear that. You know, just tell me what. Okay, well, then you're going to have to take an entire linear algebra course. You know, fun. And
Okay.
when you look at matrices and you study matrices, which is basically the entire semester of Math 254, linear algebra, I thought they were going to do algebra, and it's linear. Yeah, and that's matrices. You're going to learn a lot of stuff about fun and play with matrices. And one of the properties of square matrices is getting its determinant, which is a pure number. And I'm just showing you the process to do that.
Okay, thank you.
So let's move on. And I highly recommend that everybody in the room take linear sometime in their educational career. And if you are going to tell me, well, it's not, I don't have to take it. Yeah, you do. Like if you're an engineer worth your salt, or you're a computer scientist worth your salt, or you're a math major worth your salt, any STEM, chemistry, you name it, you got to understand linear, because one of the things of linear, total applications to machine learning, data science, engineering, control theory, all sorts. I could go on and on. Probability, stochastic matrices, or probability. Okay, let's move on. What can you conclude about the relationship between three vectors if their box product ends up being 0. That could happen. Like, oh my God, my box is 0 volume. And the answer is the vectors are coplanar. What does coplanar mean? It means they all live in the same plane. They all live in the same flat surface. Well, pictorially speaking, what would that look like? Well, it means your box is flat. Somebody squashed it. They took their foot and went flattened it down, so like here would be U, here would be V, and here would be W, and they'd be all flat on the ground. And I hope you could see that a flattened box would indeed have a volume of 0. So let's say somebody said to you, hey, how do you prove three vectors are all coplanar? The answer would be, hey, just show that the box product is equal to 0. And that would be a quick and dirty proof that the vectors are indeed coplanar. You wouldn't have to do anything further. That would be proof enough. Pretty cool, huh? Love it. Now, this was a question on quiz 1 the other day, and I know it was kind of hard, and some of you got it right and some of you didn't. How would you prove that 3 points are collinear? Now, there's a few ways to do this. The way that I'm about to tell you is not the way that you were allowed to do it on quiz 1. Well, then how come you gave it to us? Because you were supposed to do your homework and you were supposed to get the other way I wanted you to do on the quiz. And we'll discuss it right now, just because it is good to go over both approaches. When I teach computer programming, which is often, I always tell my students, hey guys, did you know that in computer programming, there's always more than one way to skin a cat? In other words, there's always more than one approach to solving some computer programming problem. And so when I grade computer programs, somebody's code, which may look completely different from a classmate's code, they both, get a good grade because their stuff works. It's just a completely different approach. And in math, that can happen too. Okay, so the way that you can prove 3 points are collinear using cross product is if you first form the vector AB. So here's A. I'll just draw 3 points that are indeed collinear. Oops, sorry. And let's say C is right here. Do you see that? That's not a very nice straight line, but that's supposed to be all living on the same line. Oh boy, I can't draw a straight line to save my life. The claim is that the vector AB, so you first have to form the vector AB given the coordinates of the point. If you take the cross product of that guy with the other vector AC, and you can even do BC, it would still work, but I'm going to just do AC. I'll just put or BC, I don't care. If it's equal to the 0 vector, that is good enough. Now, does anybody know why this is a good enough proof to prove that all these 3 points live on the same line? Does anybody want to try? If you don't get it, I wouldn't expect you to, since you're still new to learning, but I'll point out the answer. Got to do a lot of scrolling.
Is it when you multiply this something a scalar number by a vector, something like that?
It's got nothing to do with scalars because we're doing a cross product of 2 vectors. So there's no scalars involved. That would be the alternative approach, which we're not looking at right now. I'm asking you, why is it that if you show that these 2 vectors, A, B, and AC, the cross product is the 0 vector, that's good enough. That's gold, baby. You have just shown to anybody who's looking without even looking at the points A, B, and C. I don't even have to graph them. Go ahead.
Is it because 0 means there's like no area?
Sort of, but you'd still get, it's not quite that. Let me remind you of something. Sorry. Right here, number 3. Read this, please. Everybody in the room, I want you to take a moment and read this while I go replug in my Microsoft Surface Pro, okay? Read that right now. because if you understand that, you understand why that cross product equaling 0 would show that those 3 points live on the same line.
The if double f, that means it could go both ways.
Yeah. Mhm.
Okay. I wanted to make sure because like that this wasn't the one that went only one way.
No, got nothing to do with that. Now, folks, in my opinion, the difference between a good student and a great student is the following. Good students, they get pretty decent grades, like maybe B's and C's. And, they have maybe a slight inkling of what's going on, but, they listened and they can do some problems that are similar to the ones done in class. And, the great student is able to make connections. They'll learn they're able to do the problems as well,
It's
but
the
then
same.
they could take it to a higher level and be able to make some connections about facts. Yeah. So that's what I want everybody in the room to aspire to, is really try to glean some of these. And right now you're new to this, but I want to help you to make some of these connections for yourself. So you don't just you get to be where the type of student, like, I don't care, just, let me get my A and I'm out of here. If the great student isn't like that, the great student really wants to learn. They're hungry for knowledge. Okay. All right. Any other thoughts here? I'm going to explain it some more.
Isn't it kind of the same?
Well, yeah, but remember when you have vectors that are scalar multiples of each other, whoopsie daisy, what does that mean? What was the relationship between the two vectors? Do you remember that from last week?
They're parallel.
Thank you. Very good. Excellent. You're getting it now. It's starting to click for you. Awesome. They're parallel. Hello? Anybody in the room still awake? Well, how does that relate to what we're doing now? It has everything to do with what we're doing now, folks. It has everything. So if we go scrolling back, boy, we've been doing a lot in this problem here. Where are we? We're down here. So when they're saying, hey, is there a way to show that these 3 dots, these 3 points live on the same line? Sure. Form a vector AB, form a vector AC, or a vector AB and BC. I don't care. Would you agree that AB and AC are indeed parallel?
Yeah.
Yeah. And you're good to go. Now, for the quiz problem, what you needed to do when you were given those 3 points, and if you want me to do it in massive detail, please see me in office hours today and I'll be happy to do it for you, but I'm not going to do it here. But I do want to say the process was similar. You formed the vector AB and you formed the vector AC using the 2 points. You know how to do terminal minus initial, terminal minus initial. And then one of them had a couple of their components with X's and Y's in it. That was sort of the tricky part. It's like, but one of them didn't. I think the Z component for both of those vectors was a pure number. And you kind of looked and saw, if these were parallel, is one of those components a scalar multiple of the other? And you figured out what the scalar multiple was by looking at the pure numbers. And then you use that knowledge to help you get have the other 2 components have similar relationship to each other, be scalar multiples of each other with that single scalar, and then you can easily get your X and Y. Okay, it wasn't a hard problem, but it was conceptual. And the objective was I was trying to see if you could think about what does it mean, that idea of collinear does mean that you would have parallel vectors, and then parallel vectors are scalar multiples. So it was a hard problem. And if you're like, well, that was really hard, that was mean. I would put every single problem on my quizzes as hard, but I may throw 1 or 2 in there just to, do a little checkpoint to see where you're at. Most of the problems on the quiz, I hope you agree, were pretty fair. They're pretty easy, nothing crazy, stuff we did in class and so on. All right. So any questions so far now that we got that? Okay, I'm going to skip example 5. Sorry, I'm just running low on time. But if you want me to do it, it's really a cool problem. All right. It's kind of fun because you have to know two facts. This one was from section 13.3, and this fact was from the section we're doing now, 13.4. And you have to use that. I found this problem in a different calculus book, and I just thought it was crazy fun. So if you want me to do it, I'll be happy to show you. But the idea is after you do all this, what's the angle? So the unknown is go find the angle between the two vectors A and B. So here's A, here's B, whatever. And you got to get some angle, but it's not so easy because they don't give you the components. They give you the components of the cross product. So it's a fun problem, and you may want to sit with it for a while. All right, so now let's look at a funny little comic strip. I love Dilbert because when I used to be an engineer, as an engineer for 10 years, Dilbert pretty much synopsizes for me what the life as an engineer. Usually you get some boss who's not really qualified to be the boss, but he is the boss anyway, and it's funny. But I like this. Oh, you know why women are underrepresented in STEM careers? Okay, it's this guy. This guy Wally is this engineer who does zero work. He's a recurring character. And then he does weird stuff. Like, I used to cut my toenails every week. Now I just wear bigger shoes. I quit. Okay, fine. All right, now we're going to do the last application of cross product. It's a physics application. Okay, and I used to not cover this when I first started teaching Calc 3 20 plus years ago. But now I think it's important that we do it so that when you see this in physics, you're going to go, aha, I already know this. Okay, and it's not hard. Okay, so suppose you want to loosen a bolt with a wrench. Okay, that's common. You don't need to be a physics or a physicist to do that. You could just be in your garage. As you apply the force to the end of the wrench in a plane, remember that's 2D, that's perpendicular to the bolt, the twisting power, that's the twisting force, if you will, you generate depends on three things. It depends on the length of your wrench. And the bigger your length, the more power you got. So that's going to be the magnitude of R in my picture. R is the vector. That's the wrench vector right there. Okay. And then the magnitude of the force that you're applying. I'll do English, and then I'll do. So we'll do magnitude is some F. And so in this picture here, the F is right here. And then theta is the angle that the force makes with the wrench. Those are the three things that come into play when you're doing torque. Okay, the notation for torque is tau. Tau is the Greek letter for the letter T, and they use it for torque. Tau. Fine. Twisting effect. And it turns out that tau is found by taking the cross product of the wrench vector with your force vector. Okay, and the magnitude of your torque is simply the magnitude of the cross product. And from another property we learned, that's equivalent to sine of the angle between the force and the wrench multiplied by the product of the wrench length and the force magnitude. Okay, so if the wrench and the force are parallel, the sine of your angle is going to be 0, and you're not going to have any torque at all. So, if you want max torque, then have your force be 90 degrees or orthogonal to your wrench. Okay, now we're going to do a quick example here. And this is similar to what you'll see in your Briggs My Math Lab homework. So a force of 20 newtons, that's the metric system, is applied to a wrench attached to a bolt in a direction perpendicular to the bolt, which produces more torque, more twisting power. If we apply a force at an angle of 60 degrees, here's 60, on a wrench that's 0.15 meters long, or applying a force at an angle of 135 degrees here on a wrench that's a quarter of a meter long. Yeah, no, whatever. Okay, so to do this problem, you're just going to use that little formula I went over for torque, magnitude of torque, that is, and we're actually not going to do any cross products at all, because the magnitude of the torque is equal to sine of the angle multiplied by the magnitude of R, that's the length of the wrench, times the magnitude of the force. So we're going to use that formula for both. So this guy's magnitude on the left diagram I should use vector notation. And some of you lost points for not doing vector notation on your quiz. Please read your quiz. I gave you a graded version of your quiz back to you in the submission comments in Canvas. And I encourage you to look those over so you don't keep making the same mistakes over and over again. I had one student last semester, I told him, please, you need to read because I keep taking points away from you every single, exam and quiz. He wouldn't do the notation, he had really, and then he had weird calculus notation. I kept correcting him, and even on the final, did it there too. And it's like, you think by the time we reach the final, you've gotten some of the feedback and taken it on and actually learned from it. I don't know what to say to that. I'm not your mother. I'm not going to force you, but I'm just saying, sine of 60 degrees multiplied by 0.15 meters multiplied by 20 newtons, and sine of 60, I believe, is square root of 3/2. You want to whip out a calculator, and you will, I'm going to do decimal here instead of exact, about 2.6 Newton meters. Newton meters are the units, also known as, or AKA, joules, J. Newton meters, same as joules. Okay, now what about this other diagram? We've got the magnitude of the torque is going to be sine of 135 degrees multiplied by 0.25 times 20 newtons. And I get approximately 3.5 Newton meters or 3.5 joules, your favorite. So this one's the winner. There's the winner. We got a winner. So the second guy has more torque, more power there, more twisting power. Okay, now here's a little meme for you. Okay, questions. We're done with cross product. Congratulations, we're officially done with the section on cross product.
Professor, could you scroll up a little bit because I didn't get the last part.
No problem.
That was a life.
Cool.
Yeah.
Thank you.
Are we all still here?
Yeah,
Yeah.
we're here.
Are we sure? All right, I'm going to do a poll because this is how I take roll. So everybody answer this weird question. What is the strangest thing you did while attending an online meeting? Multiple choice. The voting has begun, people. Let's hit it. Ate breakfast, wore pajamas, brushed my teeth, watched Netflix. Other, but my lips are sealed. I'm looking at the results coming in here. Come on, people. We've got one person not voting. We had 11 to 12. There we go. All right. All right. We'll end the polling. So it looks like it's a tie between eating breakfast and wearing pajamas. Maybe you eat breakfast in your pajamas. I don't know. And nobody's watching Netflix while they're doing an online meeting. Okay. I'm dying to know what the other is, but we won't go there because, they're not saying. All right. So congratulations. That was an interesting poll. Fine. Okay. We're moving on. Done with that. We're going to go to the next section. So that's the cross product. Remember it. So if I were given two vectors in the plane, could I take a cross product? Yes or no?
Could you repeat that?
Yeah, if I were given two vectors in the plane, could I do the cross product on two vectors in the plane? 2D vectors, in other words. Maybe I should do another poll. Okay, in the reactions, and if you look at your Zoom bar, which you all have, one of the choices of reaction, you'll see yes or no in there. So what I want you to do right now is answer this question. Is it possible to take the cross product of two vectors in the plane? Yes or no? Answer yes or no. Click on yes or no. Look under reactions on your Zoom panel dashboard there. And then you have, you can actually click the yes, the word yes, or the word no. So,
Actually, I don't have that on my Zoom.
okay, that means that you probably don't have the Zoom app loaded on your computer, and you need to. That, because when I hear that students don't have all the features, that means you're not using the Zoom app.
Okay, I went to the website. I'll correct it today.
I have a Canvas video on my Canvas there, if you check it out, on how to download the Zoom app onto your desktop or your phone. But yeah, because you have to have it on both, because you're going to be Zooming with your phone when you take your exam. Okay, so yes or no? I have some people, only 1 or 2 people are voting here. Too scared to tell me, or you don't have the feature either? If you want, you can maybe tell me in the chat. That's okay too, if you ended up not having the feature with the yes or the no. I'm waiting. Answer the question. I don't know what I just did. Okay, we have a lot of people who may be stumped, or I don't know, maybe you're not, you don't care. Remember what I told you, the difference between a good student and a great student. Great students, they really want to understand it. They want to have a handle on it. You know, they want to know it so well they could tutor somebody else. Okay. Good students are like, give me my grade. Okay, let me go back to the cross product. Take a look at in your notes, because I'm asking you the same question. Can you take the cross product of 2 vectors in the plane? Yes or no?
No.
No, you can't, because it's meaningless. Now, for those of you like, well, I've done it, you know, I know there's a way. There is sort of, there's a way that you could say, well, if I really needed to, I could. But you would have to do something that would be extraordinary. You would have to embed the 2 vectors that are in the plane in 3D. So example, let's just say here in the XY plane, I'm just making something up. Let's say you had a vector u over here and a vector v over here. And you guys know that they only have 2 components apiece, right? And you know the 3x3 determinant method, you can't do a 3x3 determinant method if your component, you don't have a third component. So you can't do that. But if in 3D, you embed these 2 vectors in 3D, which means then you have to force them to become 3-dimensional. So the way you could do that, and this is not something that you can just do off the cuff, okay? If we gave both of those puppies a third component, which would be 0, because that's what it is if you're lying flat in the XY plane, then you'd have the vector u here, you know, and then the vector v there, and then you could take the cross product of those 2 vectors, but then that's making them into 3D vectors. So the point that I'm trying to make that's very important is that a cross product is only legit in 3D. You cannot do cross product in any other dimension. It just doesn't make sense. We don't do that, okay? So that's kind of the important thing I wanted you to get from that. So I was just doing a little testing checkpoint to see if folks were kind of getting that. And I guess I'm not doing a good enough job as a teacher here because you guys didn't get it. So I don't know what to do. All right, I encourage you to reread your lecture notes and try to stay as on top of things that we're doing as best we can, okay? So if you haven't read Monday's lecture notes, time to do. All right, so we're gonna do a new topic today. We're gonna look at lines and planes in space. What does space mean again?
3-dimensional.
3D, good, yay, 3D. Okay, fine. So we're going to look at how to get equations of lines in space, as well as an equation of a plane in space. This is a super key section. Like if you don't get this section, whew, a lot of the whole semester is gonna be no fun. Okay. So let's do lines in space first. Now here's the weird thing, because a lot of students, when I first do this lines in space, they go, oh, I already know about lines. I took algebra, you know, y equals mx plus b, baby. There's nothing more for me to learn. Yeah, there is, because y equals mx plus b, this only works in 2D. You can't use that cute little line equation in 3D. Sorry. Well, I'll just add a z in there, then I'm good. No, won't even be close. Not even partial credit. Well, what do you mean? Well, it turns out in 3D, you can't even describe a line with a single equation like you can in 2 dimensions. What do you mean? Yeah, you're going to need 3 separate equations that you wrap up in a little package, and that little package is going to describe a line in 3D. Wow, how do I get that package? We're going to go over it right now. So I'm going to derive it, and then we'll take a look here. So here's the derivation. And if you understand the derivation, you will never, ever forget the package equations. So let's say the line that I'm trying to find the equation for is that guy right there. And we're going to name him Big L. And let's say we actually can locate 2 points on that line. And it doesn't matter what points, because lines have an infinite number of points. You know, just find 2 of them. Okay. And you have the coordinates of those points. Fine. So then what? There's a vector down here called V that's parallel to your line L. You're going to need to get him. Okay, well, what if they don't give it to me? Well, there's ways of getting him, but I just want to say he's called the direction vector for your line L. And the components A, B, and C are known as direction numbers. Okay, so if you have your direction vector, here's what's going to be true. If you create the vector PQ here, so you guys know how to create a vector given 2 points. That's one of the key things we've studied so far. This vector and this vector are parallel. Okay, so that's going to be a key. So one way of describing L is to say that it consists of all the points that would be some arbitrary point Q, X, Y, Z, for which the vector PQ is parallel to the direction vector V. In English, that's what we're saying. So what does that mean? Well, it means that PQ is a scalar multiple of V, because you guys know from vectors being parallel, and that means that PQ can be written as a scalar multiple of V. So it's going to be a scalar times V. Now, in the past, I used the letter C for scalar, but now I'm going to do something a little different here. This is tradition in calculus books. I'm not going to use a C. Don't freak out, okay? I'm going to use a different scalar multiple. If you don't mind, I'm going to call it T. Well, that's weird. How come? Because T is the traditional parameter we use when we're finding what we call the parametric equations for a line. Okay, fine. But then the PQ vector, if I go, okay, terminal minus initial for the first component, terminal minus initial for the second component, terminal minus initial for the third component, and if I distribute the T over the V vector, because we're taking the scalar multiple there, and then we're going to use the equality of vectors. You know this, we did this in the first week of class. If the left-hand side vector is equal to the right-hand side vector, then what has to be true? We can equate the components. So what has to be true is x minus x1 has to be equal to TA, y minus y1 has to be equal to TB, and z minus z1 has to be TC. Those equations all have to be simultaneously true. So then what? Then you solve for x, y, and z separately, of course, and you get the 3 equations. So I'll put them kind of below here, leave some room here. So you're going to get x is equal to the x1 plus a times t, y is equal to y1 plus b times t, and z is equal to z1 plus c times t. So if line L is parallel to the vector v, I'm putting in the other information, and passing through the points P with coordinates x1, y1, z1, and Q. Q is an arbitrary point that you don't even have to have his actual coordinates. You're just giving him arbitrary coordinates x, y, and z, because he could be any point that lives anywhere on the line, and is represented, and we're talking about how the line L is represented by the parametric equations. And so these guys, folks, are called the parametric equations right here. And it's a set of 3 equations. And that's how you describe a line in 3D. You need all 3 of those equations as one big old package. Well, that looks really hard. That's ridiculous. Well, I don't know what to tell you. There's no calculus involved. We haven't done any calculus yet at all. Speaking of calculus, let me do a quick stop here for, just a pause. Now, there's another set of equations called the symmetric equations for a line, not as common. Not as common as the parametric equations. Well, what do you mean? Well, what do you do? If you solve for t, you eliminate the t for all 3 of these equations here. In other words, solve for t 3 times. And since t has to equal itself, you get what's known as this compound equation. You get x minus x1 divided by a, which represents the parameter t. That is equal to y minus y1 over b, which better be equal to z minus z1 over c. So this big old compound equation, I know it's pretty gross looking, is known as the symmetric equations for a line in space. Now, folks, I don't like this version of describing a line in space. I hate it, as a matter of fact. It's not very good. In fact, it's inferior to parametric. So how come? Well, the answer is, what if A, B, or C were 0? Even if one of them were 0. So, you don't want all 3 to be 0. What if A or B or C were equal to 0? Then you're not allowed to divide by 0 in mathematics. And so one of these expressions on here is going to be like undefined, even though the line is definitely defined. The line's doing great. So the symmetric equations are not my personal favorite, and I don't ever even ask you for that on any exam or quiz. I might give you one in the homework just so you get a feel for it, and so you'll know what it is, because I like you to be fully educated in my class, but yucky. Okay, so let's do an easy example here of finding the equations for a line in space. And we're going to do both. We're going to find both the set of parametric equations, which is my personal favorite, and just for kicks and giggles, we'll show you the symmetric, okay? And this is a super easy problem because they're giving you P, and they're giving you the vector that is the direction vector for the line. I mean, this is a super easy problem because they're giving you all the things you need. They're giving you the A, the B, and the C, the direction numbers, and they're giving you the X1, the Y1, and the Z1, the coordinates of a point on the line. So you don't even have to do any work. Like, you don't even have to engage a single brain cell. Really? Yeah. What do you mean? Look, there's your answer right there. Just plug in the X1, Y1, Z1 and plug in the ABC, multiply the ABC with the parameter. The T is known as the parameter. Is it always the letter T? No, but it's very common to have the parameter be the letter T. Sometimes it might be the letter S. Sometimes people use different kinds of weird letters. But traditionally, it's the letter T in just about every calculus book you open up. So your set of parametric equations are going to look like this. X equals Y equals Z equals. You're going to take one of the X coordinate, and then you're going to go plus, and then this direction number 2 times the parameter. The Y will be the Y coordinate plus the direction number times T. And on the last equation, Z is going to equal the Z coordinate plus the direction number times t. And we're done. That's the parametric equation. So there's your parametric. And then my unfavorite, let's do the symmetric. Ugh. Okay. Symmetric, if you look at the format here, it's a compound equation. It's stuff equals stuff equals stuff. It's got to be one big old equation. You can't have a portion of that. It has to be the whole thing. Okay, fine. So you're going to go x minus the x coordinate divided by the direction number. Okay, that's got to equal y minus a minus 2, but that's plus 2 over the direction number. Equals z minus the z coordinate all over his direction number. And boom, this is the symmetric equations right there. Not my favorite, because if even one of the direction numbers were 0, this whole thing would fall down the toilet. Okay, now here's the weird fact that you need to memorize. Right here. I'm going to give it to you. Neither parametric or symmetric equations for a line are unique. Why not? What do you mean unique? Well, in other words, there may be more than one right answer. What? And this is weird because if you take an algebra class or pre-calc, you guys know that if the answer is y equals mx plus b, you know, for example, y equals 2x plus 1, I'm just making something up. There's no other answer. I mean, there's no other equation that would describe that same exact line because the answer is unique. But in 3D, it ain't. Well, what do you mean? Well, a couple of different reasons, okay? One reason is if we look at the picture where I used the picture for derivation, what if instead of this v being the direction vector here, what if I used the direction vector was v, but we stretched him, so he was longer. That's still a vector that's parallel to the line, so he's just as good. You know, call him W. Or maybe he's pointing, I did a vector that's pointing in the opposite direction. You know, call that the vector P. I don't know, whatever. This vector is still, we could a legitimate direction vector for the line because it's parallel. And we could use his scalar components instead. So in other words, I hope you get that if you use any multiple, I'll write this down, any multiple of the direction vector v will change the look of your parametric or symmetric equations. You'll have different numbers. What's another reason? So another reason would be, hey, when you have a line, there's infinite number of points on the line. And let's say you like some point P, but maybe I found a different point somewhere on the line that was my personal favorite. And it's like, I don't like your point. Your point sucks. I like this point way over here. I'll call it Z. He's my favorite. But he still lives on the line. And my point's better than your point. Ha ha. I'm being kind of ridiculous here, but I'm trying to make a point. No pun intended. You know, and let's say my parametric or my symmetric equations, instead of the coordinates of the point that you used, hey, I'm going to use my coordinates. So right then and there, our equations are going to look different, but they're both correct. Another reason, use a different point. So what happens is when you're being asked to give the answer in my math lab has to be very savvy and accept all of the possible answers as being true. Now, sometimes my math lab will give you specific directions. So because they don't want it to be all over the map and make it easier for their software to grade. They'll tell you, you have to use this point, P, when you give the final answer and type it in. You know, you're not allowed to go find a different point. So it's like, oh man, I wanted to find a different way. Well, they'll force you to use their point. Okay, so I'm just saying, sometimes you might be forced into giving an answer that's in alignment with what they have. Okay. Now, when I teach face-to-face, which I sure do miss, don't you guys miss taking classes face-to-face? Let's take a poll.
Yes. Oh, okay.
Go to your reactions. I know you don't have the reactions, I think Kimberly told me, but then type it in the chat box. For those of you who have the yes, no buttons, click yes and no. If you would, yes meaning yes, I want to go back to face-to-face learning. No, I'm good. I like remote because I could eat breakfast in my pajamas while I'm online. Go. You're voting right now. Yes or no? Face-to-face or online? Okay, we got some people going sometimes. Jay, just sometimes. Sometimes you want to go face to face, but not all the time.
Yeah.
Okay, Nathaniel is like, meh, I'm in the middle. Sometimes. Okay, so some of you are kind of liking being at home, huh? You're getting used to it, huh? Don't want to leave the house, right? Hey, if I don't have to leave the house, it's great. I just order all my food online. I'm good to go. I know some people who haven't left the house for a year. They get all their groceries delivered, everything. They just stay inside. Works for them. I don't know. Okay. Looks like most of you want face-to-face. Some of you are okay being at home. All right, fine. So let's do another problem here. This is a super easy problem, okay? It looks hard, though. We want to get a set of parametric equations that's going to describe a line, and it passes through 2 points. So like here's your line, and there's 1 point there, and let's say here's another point here, we'll call it Q. Oh man, wait a minute, I thought I needed a direction vector and a point. And here they gave me 2 points, but no direction vector. Guess what? Good news. Your direction vector will be, we'll call it V, but we could rename it. It is PQ. You can just use the PQ vector as your direction vector, because that's certainly parallel to your line. Let's use it. So you guys know how to form a vector. Terminal minus initial, 1 minus a minus 2, 3 minus 1, 5 minus 0, and I get the component 3, 2, 5. Is that right?
Yeah, that's what I got.
Yeah. Now, would it be okay if I used QP instead of PQ? So this is just a side question. Would the vector QP also be okay to use instead?
I think so. Wouldn't it be the
Does
same?
it matter?
No, it's not.
No,
The
the
same.
answer, hold on a minute. The answer is yes, it would. Well, which one is correct? They're both going to be correct because they're both legitimate direction vectors because they're both parallel to the line L. Now, you can't use both. You have to pick one or the other. It's kind of like you got to pick a lane. I'm just picking the lane PQ because I just happen to pick it. But if you're the kind of person who thinks backwards, in this case, now, folks, when I ask you for the vector PQ, you don't give me the vector QP. Okay, that's definitely not correct. I'll give you 0 credit. But when you're coming up with the parametric equations for a line in space, and they give you 2 points on a line, as long as you give me a vector, connecting those 2 points, I don't care what order, because both of those vectors are indeed legitimate direction vectors for the line. So, but you got to pick one, okay? So I'm just going to go with 3, 2, 5, fine. Then what? Now, which one of these points should I use for those parametric equations? Should I use P or Q? Because here's the parametric equations, okay? We got the A, B, C. Those are the components of the direction vector. But what about the point coordinates, the x1, y1, z1? Should I use the coordinates for P or should I use the coordinates for Q, or what the hell?
It could be either, right?
Good, either. And I'd give you full credit. So in fact, I'll give you both those answers, heck. So let's say we use P, just because it happened to come up first. So your answer, your set of parametric equations, okay, would look like this. Okay, -2 plus, you got to have your direction number 3t, and then the coordinate 1 plus 2t, and then 0 plus 5t, which please don't write as 0 plus 5t. Just get rid of the 0. You just write 5t. That's legit. Or let's say you want to use the Q. Here's a completely different set of parametric equations that's also the perfect correct answer. Okay? Which one's better? I just told you. Parametric equations for a line are not unique, because it could have a different direction vector as long as it's a multiple, and you could use a different point on the line, and there's infinity points on a line, people. So we're just use Q's coordinates instead, and we got to use the same direction numbers though, okay? Either one of those answers is okay by me. So you can have this set of parametric equations, that's legit, or this set of parametric equations, and that is legit. Either one of those are fine with me, okay? So questions? Everybody's quiet.
What does that say? In the box at the bottom, is that an A?
Okay. There's no A's. Z equals 5. plus
No, no, no. The
5c.
box is very right.
To the right, that says or. Use Q.
Side Q.
Use the point Q. Yeah.